impedance and reactance. Circuits in which current is directly proportional to voltage are called linear circuits. For example, resistive circuits. The ratio of voltage to current in a resistor gives its resistance. As Ohm's law states that the voltage V across a resistor is proportional to current I passing through it. Now let's assume that the current flowing through the resistor is alternating current in the form of substituting the value of I in the equation, we get, therefore it can be said that where basically we can say that for a resistor the peak value of voltage is R times the peak value of current. The current and voltage are in phase, which implies that when current is maximum, the voltage will also be maximum. Mathematically, phase difference phi is equal to 0. The phasor diagram can be used to show the voltage and current in a resistor as a function of time. We can observe that phasors representing current and voltage across the resistor are both rotating with angular velocity omega. The peak current Im and peak voltage Vm are represented by the lengths of these phasors. As the voltage and current are in phase in the resistors, the value of resistance does not depend on frequency. Unlike circuits with only resistors, there are other circuits where the ratio of voltage to current is dependent on the frequency and generally have a phase difference. For such circuits, the term impedance is used instead of resistance. Thus, impedance is the general name given to the ratio between voltage and current. It is represented by the symbol Z. Note that resistance is a special case of impedance. Now to understand reactance, consider the special case in which the voltage and current are out of phase by 90 degrees. This is an important case because no power is lost in this condition. In these cases, the term reactance is used. Thus, reactance is the ratio of voltage to current in the cases where the voltage and current are out of phase by 90 degrees. It is represented by the symbol X. Note that the difference between reactance and resistance is that reactance is frequency dependent. In case of capacitor, we have studied that the voltage depends on the amount of charge stored on its plates. From the definition of capacitance, we know that, considering that current I is alternating in nature, we have, substituting this value of I in the above equation, we get, upon integration, we get, or the term implies that the current phasor is leading the voltage phasor by 90 degrees. Therefore, the phasor diagram of a capacitor is as shown. We can see that both current and voltage are out of phase by 90 degrees. Mathematically, phi is equal to 90. The ratio of the magnitude of the voltage to magnitude of current in the capacitor is defined as capacitive reactance Xc. From the equation, we can see that Xc is equal to 1 by omega c. The terms of the equation can be rearranged in terms of Ohm's law to get a direct relation between peak voltage and current. Now from the equation, it can be deduced that the capacitive reactance Xc decreases with an increase in frequency. In case of an inductor, the voltage that appears is due to its own magnetic field, and in accordance with Faraday's law of electromagnetic induction. The current IT in the coil sets up a magnetic field of magnetic flux omega B, which is proportional to the field strength and the current flowing. Faraday's law gives the EMF as, this EMF is a voltage rise. So for the voltage drop VL across the inductor, we have, mathematically, phi is equal to 90. Now considering that the current I is alternating in nature, and substituting the value of I in the equation, we get, on differentiation we get, this term implies that the current phasor is lagging the voltage phasor by 90 degrees. The phasor diagram of an inductor is as shown. We can see that both current and voltage are out of phase by 90 degrees. Mathematically, phi is equal to 90. The ratio of magnitude of the voltage to magnitude of current in the inductor is defined as inductive reactance XL, which is equal to omega L. The terms of the equation can be rearranged in terms of Ohm's law to get a direct relation between peak voltage and current. From the equation, it can be deduced that the inductive reactance XL increases with frequency. We can summarize the impedance of different components with the help of a table. Note that the voltage on the capacitor is behind the current because the charge doesn't build up until after the current has been flowing for a while. In the case of inductor, the voltage leads the current. The frequency dependence of different impedance can be compared using a plot. Note that at zero frequency, inductance is a short circuit, and so its impedance is zero. Also at zero frequency, a capacitor is an open circuit, so its impedance goes to infinity. The impedance of a resistor is constant, as it does not depend on frequency. Related term is